Hello everyone. So now that we have worked with obtuse triangles and right triangles, let's see if we can show stuff with acute triangles. So we have triangle ABC, and we have that angle B is strictly greater than angle C. We want to prove that AC is greater than AB. So let's label some points: A, B, and C. Alright, now how can I show that the side AC is greater than AB? Well, one of the ways we have solved all these problems, or just about any problem, is to try to make some right triangles. So I'm going to drop the altitude, the height, and get a right triangle out of it. So this is going to be our right angle. I'm going to label this point X. And in the past, on these problems, we have used the Pythagorean theorem. So I could say like AC squared is equal to, we have XC squared plus AX squared. And another one I could write would be that AB squared is equal to bx squared plus ax squared. Now, I could try to say that if xc is greater than bx, ac has to be greater than ab, because both equations have the same ax number here, which means that if this number is bigger than this number, then that means that AC would have to be bigger than AB. But how do I know for sure that BX is less than XC? I mean, it looks like it is, but how do I know for sure? Well, we can't prove it, so let's try some sort of different approach. So let's say if I were to extend BC outward, and what I want to show is that AC's length is longer than AB's length. So let's say I came up with a new point like D somewhere on this line that has the same length as AC. I want to show that that length cannot be located inside the triangle ABX. It has to be located on the outside somewhere over here to show that it's longer. So let's imagine, I don't know right now that it is, but let's imagine there is a point D somewhere on the line BC, and I have to show that it is strictly bigger than, or what I want to show is that if I assume that such a point exists and that AD is equal to AC, I now want to show that AD is bigger than AB. Well, how could I do that? Well, this triangle would have to be an isosceles triangle if we had such a line. So, triangle ADC is isosceles, and angle D is congruent to angle C. Now again, I know I have the diagram. I know that I drew it so that D is outside. It looks longer, but don't get too caught up in that. Try to imagine that the line AD is in some point. It could be here, or it could be like this red point here. That could be the real point D. I don't know that it's past B. That's what I'm trying to show. So all I know is that if I do have such a line where this is true, then that means the triangle created by it, ADC, would be isosceles, with those two angles being the same. So these two angles are the same. Now, what does that tell me? Well, since point D is on the other side of X, either beyond B or not beyond B, but it is past X. So, I know that the angle D is equal to, well, it's a part of this right triangle ADX. So therefore, it's equal to 90 degrees minus the angle DAX. That is what I know that angle D is equivalent to. Now, angle, it was just angle B, but angle, we have to be a little more specific now. ABX is equal to 90 degrees minus the angle BAX. And since we have that the angle what would it be? Angle ABX is greater than angle C. That's just this part here. I know I'm calling it ABX now, but this is ABX. That angle is the original angle B in our diagram. Because we started that as a given, we know that that's greater than angle B. We know that angle ABX is greater than angle D, because angle D and angle C are the same. It's that transitive property. So we have that. Thus, well, we know angle D is 90 degrees minus the angle DAX. This must be less than, is less than 90 degrees minus angle BAX, because that's what angle D is equivalent to. It's the angle D 90 minus DAX, and that's less than angle ABX, which is 90 minus BAX. So if we kind of treat this as an equation, now it's going to be a little confusing because my angle sign looks the same as the inequality signs, but since we have that 90 degrees minus angle DAX is less than, I'll try to make it a little smaller, 90 degrees minus the angle BAX. If we remember from algebra, we can just subtract 90 on both sides, and we'll get that negative angle DAX is less than negative angle BAX. And if I change the signs, but remember, if you change the signs, you have to flip the inequality sign. This is going to actually imply that angle DAX is greater than angle BAX. Or you could think of it as if I added BAX over to this side and added DAX over to that side of the inequality. That would produce this. So, why is all that important? Why is this important? Well, if the angle DAX, this angle, has to be greater than BAX, this angle here. If that is true, then that means that the point D is farther away from X than the point B is. So, let's move on here. This implies that this is implying that the point is a farther distance away from X than B is. Because the angle that DAX is making is larger than the angle that I'll draw in red, ABX is making. And since it's a greater angle, that means the point D is farther away than B is. Now, because that this is true, this is implying that the distance of, so we have that this implies that DX is strictly greater than BX. And since it's an isosceles triangle, we have that DX is equal to XC. So XC is strictly greater than BX. And going back to what we had earlier, since XC is greater than BX and AC is greater than AB, because of that, since they're both AX added with the numbers XC or BX respectively, that means that we have that AC squared is greater than AB squared, which implies that AC is greater than AB. And that concludes our proof. And I mean, logically, since D is further away from B, that alone implies that AD is greater than AB. But this is the hardcore explanation of it, I guess. So now we know that in an acute triangle, comparing two angles, if one is greater than the other, the opposite side must be greater.